Okay, so we're solving for the second eigenvector. We get the augmented matrix, row operation to echelon form, and we choose y equals 2 for the form we get, so we have v2 equals 1, 2. So this result and this result gives us the eigenvectors and eigenvalues. Okay, so now, so you can go and do what we need to do, say a 3x3 example, another example. Let's do 1, 0, 0, say, let's see what this could be. 2, 3, and then 1, 2, 2, 1. Let me see. Yeah, let's do that. Okay, so here's our M. So we need to write down the formula for the characteristic polynomial. So you write down determinant of 1 minus lambda, 2, 3. Oh, let's make this just in case this is nicer. Let's put a 4 in here, just so we have a better chance of having something reasonable. 0, 1 minus lambda 2, and 0, 0, 2 minus lambda.
Is that 2, 4?
Oh, this is a 1 here. Excuse me?
Is that a 2 and then a 4 you put at the top?
Yes, okay. This is badly written. Let me see if I can write this more clearly. 1 minus lambda 0, 0, 2, 1 minus lambda 1, and 4, 2, 2 minus lambda. Okay, and this is going to equal 0. So to do the determinant, one way to do is to use the special rule where you low mark plus, minus, plus, right? What we're going to do is, though, we could do that. Let's instead do this. We're going to expand along the first column. So we write our plus, minus, plus down here. And so what it's going to be is we're going to write it as 1 minus lambda, this term here, times the determinant of this part here. So I'm going to try to highlight that. This first one here is this little blue there, this one. So this is going to be 1 minus lambda, 2 minus lambda, minus 2. Okay? And then it's going to be minus 0 just so you know the formula, it will be minus 0, right? And the 0 is going to like sort of it's going to be the determinant of this with this. So you can sort of see 0 times 2 times 2 minus lambda. Of course, this is going to go to 0, but just you can sort of see 2 times 2 minus lambda times 1 times 4, right? And then we would do plus 0. Let me use a different color. Plus 0. That's this one here, right? We would do this one here would then be doing the determinant of this piece up here, right? And that would be the determinant of 2 times 2 minus 4 times 1 minus lambda. Okay? I just wanted to so you can sort of see, you want to choose to do the determinant in the simplest way possible. If you ever you have something with lots of zeros on it, you can do that and it'll chop out. It would have worked okay. You just would have, the zero would have been less obvious the other ways. Okay. So we can write out this. So the result's going to be 1 minus lambda times 1 minus lambda 2 minus lambda minus 2 equals 0. And then we have to write all this out. So it's going to be, well, right away we can see that 1 minus lambda is one of the factors, right? Because that's multiple. So one of the eigenvalues is going to be 1. We multiply, this is going to be 2 plus lambda squared minus 2 lambda is minus 3 lambda minus 2 equals 0. So we end up with 1 minus lambda. The 2's here cancel, and we end up with lambda times lambda minus 3 equals 0. So we end up with lambda 1 equaling 0, lambda 2 equals 1, and lambda 3 equals 3.
Would it be negative 1?
Well, lambda equals 1 to make this 0. It does, the left, in other words,
Yeah, that'd be right.
1 minus lambda equals 0 has the same result as lambda minus 1 equals 0. So is that, unless it was a plus, unless I missed a plus sign somewhere. It would be if we had a plus sign in here instead of a minus sign.
Yeah.
The problem is it's hard to write down matrices that have real eigenvalues that are integers just off the top of your head. So I have to do something that makes them sort of ultra simple to do that, but then they're not the most obvious. We can go to the textbook and get another example from there that would be more, that will give us a little bit more run for our money. Okay, so then you have 3 wonderful equations. We see 1, 2, we have 1, 2, 4. 0, 1, 2, 0, 1, 2 times x, y, z equals 0, 0, 0 as the one for lambda 1. So we can just write down, so we can do, so the augmented matrix is right away 2, 4, 0, 2, 0, 1, 2, 0, 0, 0, which we then can do minus row 2 plus row 3 to get 1, 2, 4, 0, 1, 2, 0, 0, 0, 0, 0, 0, right? And so we have to do back substitution here to, or we can do it to do, this is x, y, and z. So we have y plus 2z equals 0. So y equals minus 2z. I think I'm just checking over to make sure. Okay. If you spot any errors, tell me. X plus 2y minus 4z equals 0 is the top equation, and that says that x equals minus 2y plus 4z, right? Plus 4z minus 2y. But then I use the y here. This is going to equal minus 2z for y would be.
I think the x plus 2y plus 4z equals 0.
Well, this is going to be plus here, right? So you're going to have, let's see. You can have 4z plus 4z equals 8z, right?
But I think, going back to the previous, to the left.
Oh, this is, why did I put a minus sign? I wrote a, somehow I want to, why did I put a minus sign there? Yeah, so there, so that one makes things, yes. Okay, so if that's true, then this would be minus, and then this would be 4z minus 4z equals 0. So therefore, my possible eigenvectors are 0, y is minus 2z, and z, right? So let's just choose z equals to be 1. And then also we can check. Let's say that we have v1 equals 0 minus 2, 1. Now we can check right away, and probably it's a good idea to check. This is 1, 2, 4, 0, 1, 2, 0, 1, 2, 0 minus 2, 1. So we can do the matrix multiplication and see that we should get 0 times this vector, right? So let's see what happens. Well, it may be trivial because this vector, okay, well, let's see. We end up with 1 times 0, 0. 2 times minus 4 is 2 times minus 2 is minus 4. 4 times minus 4, we get 0, right? This is going to be 0 times 0 plus 1 times minus 2 plus 2 is 0, and 0 times 0 minus 2 plus 2 is 0, which equals 0 times 0 minus 2, 1. Although it seems a little bit like cheating, right? But it works. Whenever you have a 0 eigenvector, it's as long as this works, then it's going to do that okay. Okay, well, now on to V2, right? So that's going to be, what is lambda 2? Lambda 2 equals 1. So we have 0, 2, 4, 0, 0, 2, 0, 1, 1 as the augmented matrix for the system, right? I took the matrix, subtracted ones, that gives me, I'm going to diagonal it, they give me 0, 0, 1 there. So that's just, okay. And you can, let's see. Well, we can, let's just go ahead and do it officially, even though we could probably guess some of the ideas. We can swap row 2 with row 3 to get 0, 2, 4, 0, 0, 1, 1, 0, and 0, 0, 2, 0. And then we can do, I'm not sure why I did that exactly. Okay, but then we can do minus 1/2 row 1 plus row 2. Yeah, that was probably superfluous. 0, 2, 4, 0, 0, and then 1/2 times minus 2 times minus 1/2 is minus 1, so you get a 0 there. And 1/2 minus 1/2 of 4 is minus 2 plus 1 is minus 1. And 0, 0, 2, 0, 0. So then we can do 2 times row 2 plus row 3. Get 0, 2, 4, 0, 0, 0, minus 1, 0, 0, 0, 0, 0. Right? Okay, well, that means that the second equation is minus z equals 0. And which obviously we did something that was wrong, right? Because we're going to get, if this was true, we would end up, if this was true, we would end up with, oh no, that's okay. This is okay. Yes, it's okay. Minus z equals 0. It's a little bit, it's like sometimes these equations turn out this way. Then it would be y 2y plus 4z equals 0. But since z is 0, y equals 0, right? So all the forms that we have are x 0, 0. So we choose x equaling 1. The point is, in this form, this is one of these weird matrices in which the first variable x is free, right? Y is leading and z is leading, but x is free. So we choose x equals 1. So we have v2 equals 1, 0, 0. Well, we can check. This is a more interesting check for the eigenvector equation. 1, 2, 4, 0, 1, 2, 0, 1, 2, 1, 0, 0 equals, well, 1 times 1 is 1, then 2, 0, 4 zeros, 1, and then the second row here is 0 times 1, 1 times 0, 2 times 0, 0, 0 times 1, 1 times 0, 0 times 2 times 0, 0, which obviously equals 1 times 1, 0, 0. Okay, so that holds. And we now get to do even more fun by finding v3, for which lambda 3 equals 3. So we have 1 minus 3, 2, 4, 0, 1 minus 3, 2, and 0, 1, 2 minus 3, 0, 0, 0. Okay? So that gives me the form minus 2, 2, 4, 0, minus 2, 2, and 0, 1, minus 1. Do you guys spot any errors? Okay, so this one, we do 1/2 row 2 plus row 3, minus 2, 2, 4, 0, 0, minus 2, 2, 0, and that's going to produce all zeros, the bottom row. And that's an echelon form. So we have, this is like x, y, and z, so we have minus 2y plus 2z equals 0. So that's the same thing as y equals z, right? To be 0, that y has to equal z, okay, because we're solving for then the last one is minus 2x plus 2y plus 4z equals 0. So therefore, x equals y plus 2z. So if I do that, I'm going to get minus 2y minus 4z. Okay? And then, since y is z, this is going to equal 3z. So I think that the eigenvectors I get are x. No. You see an error?
Oh, so you just divide by 2. Okay, that's it.
Yeah,
You just took out 2.
yeah, there's a 2 that gets taken out here. Because I can, yes. Also, if I put this back in here, just substitute this back in here, I'm gonna get a -2y to cancel that, and then a -4z to cancel that. Okay, so I have here 3z, z, and z, so I can choose z equals 1 to give me v3 equals 3, 1, 1. Is the simplest. Okay, good. So I have lambda 3 equals 3 with v3 equals 3, 1, 1. And we can then check with 1, 2, 4, 0, 1, 2, 0, 1, 2 times 3, 1, 1 and see what happens. Well, this is going to be 1 times 3 plus 2 plus 4. 3 plus 2 plus 4 is 6, is 9, I think, right? 3 plus 2 plus 4 is 6, 7, 8, 9. Okay, the second one is 0 times 3 plus 1 plus 2 is going to be 3, and the same thing here, 3, so then I can factor out a 3 times 3, 1, 1. So this one seems more like something non-trivial happened, right? Okay, well, so should we do even more fun and try a 4x4 matrix? Then that means you have to find a fourth order polynomial with then 4 linear systems to solve, right? And that's not much fun, right? You can see right away that, okay, but there's, now, let's see. Let's look in the text to see whether this is all in there. Characteristic polynomial, everything I'm just looking for. There's something I haven't done. I've chosen things where you can have repeated roots. And funny things happen. I mean, things happen with repeated roots that you can have like you can have one eigenvalue with a 2-dimensional eigenspace. So there's all kinds of special things that can occur, like in this case here, right? Okay, so we haven't dealt with that case, but I wanted to go. Let's go through and find some. I wanted to do this to find an example. Like here's a 3x3 one that's messy, right? Look at that polynomial. Okay. Let's find. So there's more examples here of this whole process. Well, that's not many fun examples, is there? Okay, well, let's do. Let's see.